His hand. And please bring up the pencils if you don't mind. We like to reuse and recycle. Alright, as the last people turn in their trivia sheets, I will introduce our first speaker of the night. She is a rising third-year graduate student in the astronomy department of the University of Washington. Please give a warm welcome to Kathryn Neugent.
Thank you. So, as Nicole just said, I'm a third year at UW, and I work on massive stars with Emily Levesque, who's sitting right over there. So today I'm going to tell you a little story that has some ups and downs, some excitement and some sadness. It's not very spooky, so I've tried to kind of adjust for that with the text and the friendly ghosts that you'll see throughout the presentation. So I apologize for the lack of spookiness, but this is what happened. So today I'm going to tell you about the extragalactic yellow supergiant that wasn't, but was something even better. So the story starts around 10 years ago, October 2009, in a remote mountaintop in Chile at Lowell International Observatory on a cloudy 5-night run. And so my collaborators, Maria Drought and Phil Massey, were searching for yellow supergiants in the Small Magellanic Cloud. And so the Small Magellanic Cloud, which was actually just in our trivia, is a irregular dwarf galaxy that is, you can see in the southern hemisphere. If it's dark, you look up into the sky, you can see a small little blob on the sky that's the Small Magellanic Cloud. It's around 8 times smaller in radius than our Milky Way, and they were searching for yellow supergiants in this galaxy. And so, because this is an astronomy talk, we have to have our favorite HR diagram. And so, is this the pointer? Here we go. And so we have temperature on the x-axis, luminosity on the y-axis, and I just want to tell you what a yellow supergiant is before I spend the rest of the talk talking about it. So here we have yellow supergiants located up here in the upper right-hand corner. They're pretty cool, around, not just in temperature, but also, they're awesome. But they're around 4,000 to 5,000 degrees Kelvin, and they're very luminous. So they're massive stars that are 8 to 30 times the mass of the sun on the main sequence. So when they're O and B stars over here that have burned through their hydrogen, they've evolved off the main sequence, and they're going through this very short-lived phase called the yellow supergiant phase. And it's tens of thousands of years. And so this is very short in astronomical timescales. And so they're going to be yellow supergiants before they turn into red supergiants, and then eventually end their lives as supernova. So when you're looking for yellow supergiants, one thing that you can see is they're not the only yellow stars in the sky. They're really bright, but there's also other yellow stars, like our sun. And so we need a way to separate out the yellow stars that are the yellow supergiants and the yellow stars that are lower in mass. And when we're looking at another galaxy, such as in this case the Small Magellanic Cloud, that's made kind of difficult because we are looking at the other galaxy, and we're also looking through our own galaxy. So here's, say this is the Milky Way, this is happy little Earth, and we have our telescope, we're looking at another galaxy. So we're going to see the really bright yellow supergiants in the other galaxy, in this case the Small Magellanic Cloud, as well as, but they're far away, so they're going to appear less bright. And then we're going to have the smaller, but still bright, yellow stars in our own galaxy. So we need a way to separate out the stars that, and in this case, we're interested in the yellow supergiants versus the foreground yellow stars. And so to do that, we can use how fast they're moving. And so the Small Magellanic Cloud is traveling, its systemic radial velocity is the official terminology, is around 160 kilometers per second. So any star that we see that's moving that fast is probably in the Small Magellanic Cloud. And any star that we see that is moving more close to 0 kilometers per second is in our Milky Way. So this allows us to distinguish the yellow supergiants in the Small Magellanic Cloud from the yellow stars in our own Milky Way. So this kind of sets the stage. Maria and Phil went and observed a bunch of spectra, and then I came along and I wrote up my first author paper way back in 2010 about these stars, and everything was all happy. I was happy. I had a paper, and this all just kind of went by the wayside for around 8 years. When I went back and looked at this plot, and because I couldn't remember how fast the SMC was moving, and I saw this. What is this? What is this point that is moving at 300 kilometers per second? So I looked at the spectra and looked like a yellow supergiant. It's moving pretty fast. So I decided that this was the first runaway yellow supergiant that had been discovered, which was pretty exciting. Other massive evolved stars that were runaway, there was one other one that had been discovered, but this was the first yellow supergiant. And so, knowing the distance and the magnitude and all of that good stuff, I could find some of its physical parameters. And so, the kind of cool ones here are that it is 9 solar masses, so kind of just on the edge of being a massive star, but it's 200 solar radii. So something that is 200 solar radii is speeding throughout space at 300 kilometers per second. That's pretty cool. So here it is where it's located in the Small Magellanic Cloud, way out in the boonies. And this red circle shows how far it probably traveled throughout the course of its life. If you assume that it, basically was always moving at 300 kilometers per second. But how did that happen? And so going back to what is a runaway star? Why do these things occur? They were first written about and hypothesized in the 50s and 60s. Dr. Blau wrote the first paper on runaway stars. And the idea is that there are 2 main mechanisms that create these stars that are moving much faster than they should be. And so the first is a supernova explosion. So you have 2 stars in a binary system. One of them is a massive star and evolves, and eventually it explodes, and its companion will then get shot out into space. And so obviously this will make stars move very quickly throughout space and then eventually become unbound from where they were born, causing a runaway star. And the other one is what they call a dynamic interaction. So basically there's multiple bodies all close together. They're interacting with each other, they're perturbing each other's orbits, and eventually it will cause one of the stars to speed off into space. And recent research into this has shown that the dynamic interactions actually cause stars to move faster. So stars that move faster than 30 kilometers per second are usually caused by dynamic interactions and are called runaways, whereas supernova explosions actually tend to produce kind of slower stars, which they've called walkaway stars. So I find that funny. So the question was then, what produced this runaway yellow supergiant? We didn't really have enough information to determine if it was a supernova or dynamic interaction, but these are kind of two of the main possibilities. One favorite runaway star that we all hopefully know and love is Betelgeuse. And so here's the constellation Orion that we can see in our nice winter sky. It is the Armpits of Orion. And it's actually pretty cool. You can image it in the infrared and actually see its dust creating a bow shock. And so red supergiant stars are incredibly dusty. They puff off a lot of material. And so this is actually the dust that has been puffed off the star moving at around 30 kilometers per second and interacting with the interstellar material in front of it. And so you get to see this nice bow shock. And so you see that in some, but not all runaway stars. So this was, as I said, exciting for me. We had a press release, and it got a lot of attention. And so here is a Newsweek article talking about how this star is speeding across a neighboring galaxy at 300,000 miles per hour. And it was on I Freaking Love Science. Had to be polite there. And it got around 5,000 shares. And Sky and Telescope did something on it, UW News. And I was even interviewed by an Australian astronomer for a podcast, which was pretty funny. So, I presented a poster. Basically, I made a big deal about this thing because it was fun and it was a nice little side project from some of the other research I was doing. And I wrote another paper, so we're all happy. And then the field of astronomy was revolutionized by this new instrument called Gaia. And so Gaia is very exciting. It is a spacecraft that is looking at the positions and proper motions and parallaxes of over 1 billion stars. And what it's doing is it's getting the distances to these stars, which is really important because if you have your telescope and you look at a star, you're going to see its apparent magnitude. But in order to know its absolute magnitude and learn more about what type of star it is, all of that good stuff, you need to know the distance. And so Gaia is giving you this information. And so, just kind of on a whim, I decided to look in the Gaia database and see if it said anything for my star, for my nice little runaway yellow supergiant. So here is the RA and the deck, which are its positions in space. And here is a parallax in milli arc seconds in the error. And from that, you can get a distance. So the distance came out to be 9 kiloparsecs. So this presents a problem. The distance of the Small Magellanic Cloud is 59 kiloparsecs. So this star that I've done papers and posters and press releases and podcasts about is not located in the Small Magellanic Cloud. It's moving very fast and it is yellow, but it is not in the Small Magellanic Cloud. So where did we go wrong? What was the issue? And is this star still interesting in any way, shape, or form? So 9 kiloparsecs puts it in the halo. And so here is a very basic diagram of our Milky Way galaxy. And so it is located out here in the halo. It is still a very luminous star, and so it is a giant. It's a yellow giant. Here is a plot that the one on the right is kind of the more interesting one. The plane is coming out towards you, and it shows that the star is around 6.5 kiloparsecs below the disk of the Milky Way. So according to Gaia, the distance that we get from the parallax, this is a halo yellow giant star. And so this, of course, the distance changes the absolute magnitude, changes the luminosity, changes the radius, changes the mass, changes basically all of the physical parameters that we had decided on. So these are the new ones. Little less massive, 3.5 solar masses. Still kind of big, 32 solar radii. Much, much older. It's a smaller star, and so it's 180 million years old. And from this, we can learn more about the star. However, originally I looked at the spectra, and I said, yeah, that looks like a yellow supergiant. And guess what? This does not look like a normal halo star. There's something weird about this star. And so here is the spectra of the star, and what I want you to notice is that there's a bunch of stuff in here. And this stuff, these are metal lines. And you wouldn't usually find these lines in a normal halo star. Halo stars are very metal poor. There haven't been a lot of star formation, massive stars to explode, to enrich the interstellar medium to create new metals. And so you don't expect to find a metal-rich star in the halo. You do expect to find a metal-rich star in the disk of our galaxy. So here we have a star that's moving at 300 kilometers per second, that is slightly more massive than you would expect, and has more metals than you would expect. And this is its projection for the direction that it's moving in. This little arrow shows how far it would move in 10 million years. And so if we kind of just naively work backwards, well, it looks like it's coming from the galactic center. And what's in the galactic center? A black hole. So that's kind of exciting. So we went to our colleagues that actually do like dynamics, because we are observational astronomers. We take pretty pictures of the night sky, but other people actually do, like the physics behind it. So we went to Steve Levine at Lowell Observatory, and he was able to, using all of the information that we had, try and figure out where this star actually came from. And it turns out that this star interacted with the supermassive black hole in the center of our galaxy. And so that's pretty cool. It started out here in the plane of the Milky Way, and interacted with it as it passes through the center. It's now located down here, 6 kiloparsecs out in the halo. And so this is the first case, and remember this is right after Gaia came out, and so there have been many other cases since then, but this was the first published case where a star was confirmed to be ejected from the galaxy's supermassive black hole. So that was pretty cool. And this had been hypothesized by many, many people. There are stars that are moving thousands of kilometers per second, and the only way they could get that fast is by interacting with something like a massive black hole. This allows plenty of other science to be done. We were excited to find out that someone actually wrote a paper looking at the shape of the dark matter halo based off of this one yellow giant that we found. And so now that there are, I think, on the order of tens of these stars that have been found, stuff like this can be better constrained. And so I just want to leave you with this Nathan Pyle comic that kind of describes how science works sometimes, in that you're wrong. And sometimes you're wrong, and you have press releases and papers and posters and lots of exciting things. But then new stuff comes along and you find something even better. So that's my story of the yellow supergiant that ended up being something even cooler. Thank you. Are there any questions? Yeah, come up closer and.
When Gaia came out, did that like expose a ton of other information about stars?
Yes.
Or was it, like, just yours?
Oh no, so many. Actually, there was a whole class of hypervelocity B stars that were written about that were supposed to be moving at like tens of thousands of kilometers per second. And Gaia came out and showed that all of that information was wrong, and they were actually moving at like 20 kilometers per second. Gaia really revolutionized a lot of astronomy in a lot of different ways. I think there was another one back there somewhere. Yes.
Hi. Are you doing any more work on this particular star, or is this sort of like the end of the story?
As of right now, it's the end of the story. There are other stars that we have radio velocity calculations of that appear to be moving really fast. And originally we were like, oh, they're runaway massive stars. And so definitely going back and looking at those and being like, are they not, would be interesting. But so far we've kind of passed it off to other people. And yeah. Sorry, the question was how close it came to the black hole. I don't actually remember. We definitely did that calculation. I just don't remember it off the top of my head. But not, I mean, like, it didn't go all the way up to, like, the event horizon. It just went within it enough to perturb its, the direction that it was moving in. So it didn't go close enough to get, struck apart. I think we're good.
congratulations again to our trivia winners. Our next speaker is not only one of the co-organizers of Astronomy on Tap, he is also a fifth-year graduate student at the University of Washington in the astronomy department, and he is the drummer in the premier all-astronomer band in Seattle, Night Lunch. Please give it up for Trevor Dorn-Wallenstein.
Thank you so much. What Nicole does not mention is that she's the lead singer in Night Lunch. All right, let's see here. Laser pointer. Ghost. Awesome. We're ready to go. So, Nicole, thank you for the introduction. Like she said, my name is Trevor Dorn-Wallenstein. I'm a fifth-year graduate student at the University of Washington. And today I'm delighted to bring some Halloween horror to Astronomy on Tap. Oh, God, they're behind me. Oh, no. So I love Halloween, right? October's awesome. We get the fall colors. We get the kind of cozy, like, flannel weather. I love flannels. We get nice cool rain and fog or whatever was going on this morning. We get to dress up in these awesome costumes. Does anybody watch Over the Garden Wall? Excellent. And so when I found out that I was giving the October Astro on Tap talk, I thought, well, of course, I gotta give a spooky, scary talk about spooky, scary space ghosts. So what am I going to talk about? I could talk about Thorn-Jitgob objects. These are massive stars that have swollen and evolved and swallowed the dead corpses of their stellar neighbors. Ooh, I love it. I can talk about Supernova 2009 IP, which in 2009, you might go figure from the name, exploded and died. And then came back to life in 2012 and exploded 2 more times. I could talk about some superluminous blobs. For whatever reason, I thought that was a good idea. It wasn't. I can talk about the Ghost Nebula. Look at these ghosts. They're so mad that I'm not going to talk about them. Then I remember the last time that I was here to give an Astronomy on Tap talk. Was anybody here for this talk in July 26th of 2017? The real spooky space ghost is the passage of time. So, if you were there, you would have heard me talk all about the astrophysical origins of beer. But my favorite part about this talk is that while I was talking about beer, right, we're all here at a brewery, or a lot of people here like beer. But along the way, I snuck in some nuclear astrophysics. That was pretty fun. I just kind of sprinkled it in. We're all nuclear astrophysicists now. And so I thought, all right, it's Halloween. I'm going to give a spooky talk, and I'm going to sneak in a spooky, spooky science space ghost. What is that space ghost going to be? All right, I haven't practiced the timing on this, so I hope it works. All right, everyone with me here? Cool. It's... geometry. No, come on. Alright, so let's forget about geometry though, because that's too scary. We're going to go and bring it back down a little bit and tell 2 ghost stories. The first is the tale of V838 Mon, and the second is the mystery of Hanny's Vorwerp. So let's get right to it. The tale of V838 Mon. This is not Monty Python and the Holy Grail, but I so totally wish it was. So before we get to V838 Mon and what it is and why it's awesome, let's take a look at the night sky. Has anyone been to kind of a dark sky site and looked at the sky? A lot of us here, we're all astro nerds. If you have not, I highly recommend it. Because when you go out away from the city lights and look at the night sky, you see something that looks like this. Anybody who's seen this tableau, what are we seeing? What's in this image? Just shout it out. Stars. Milky Way, yep, this is our Milky Way galaxy. It's composed of stars, and kind of across this milky band of stars, there are these dark patches where there appear not to be any stars. Let's zoom in and take a look at one of these. This is Barnard 68. It is a Bok globule, after the person who named them after himself. Go figure. And here's what's going on. So we see a very dense field full of stars. We see this dark cloud through which no stars can be seen, and around the edge, some stars that all appear kind of red. And so, all told, we think that this, or we know rather, that this is a cloud made out of gas and dust. And all that gas and dust obscures the starlight, which is why we can't see any stars through the dense center of this molecular cloud. But it also reddens the starlight. It takes the starlight and kind of systematically gets rid of the blue light to leave behind red light. All right, so let's talk about dust. Everyone's favorite, space dust. Right? Yeah, awesome. So, space dust can be modeled more or less like individual grains of rice. It's made up of these kind of big, long molecules, or sometimes compounds of multiple different molecules, and it has a long end and a little skinny end. And so if you're a photon, if you're a little blobit of light, and you're coming down from the top, you're going to see the skinny, tiny, pointy end of the dust grain, and so you're probably just going to whiz on by. But if you're coming at it from the side, you see the big, wider end, and you're more likely to interact with the dust grain. Now, when you interact, you can either get absorbed, or you can get scattered, like a billiard ball, off of the edge of a pool table. And so in kind of this belt around the center, around the wide end of this dust grain, you're more likely to get absorbed or scattered and be emitted. Okay, so scattered. Why do we care about scattering at all? Because for the most part, dust grains are kind of randomly oriented, right? There's no preferential alignment to these little grains of rice, these little needles. And so for photons, all of which are coming... Did that work? I hope it worked. Awesome, cool. For photons coming from random directions, we don't really pick out that long angle. We don't really prefer that long angle at all. Of course, there's a way to line up dust grains all along with each other. That's via magnetic fields, much like iron filings around a bar magnet. Dust grains can line up along the galaxy's magnetic field. But another way is with a source of light at the center of some kind of randomly distributed grains of dust. Now remember that light likes to see the big wide end of a dust grain. And so for a central source of light at the center here, we're going to preferentially pick out the dust grains that are showing their wide sides towards the center of this light source. Everyone with me so far? Great. Let's look at this in action. Ooh. Cool, right? That's kind of spooky, right? It kind of looks spooky. You're with me? This is spooky, cool, spooky space ghosts. Great, awesome! So, what's going on here? This is V838 Mon, and in 2002 it went through an outburst. It got a lot brighter. And so scientists followed up with the Hubble Space Telescope and took this collection of images from which that cool-looking GIF was made. And in this collection of images, we can kind of see this expanding shell of stuff. But here's the thing, we know how far away V838 Mon is, roughly, and we can see how far this expanding shell of stuff looks, or how fast this expanding shell of stuff looks like it's expanding. And so you can figure out from the distance and how fast it looks like it's going, how fast it's actually going, and it's moving at about the speed of light. Now, V838 Mon is actually a red supergiant, kind of like the yellow supergiants that Kathryn was looking for, but a little bit cooler. Sorry, no shade, because there's stars, there's no shade. Now, red supergiants do eject mass, but they eject mass in these very dense but very slow dusty winds, and so that couldn't be what's going on. See, what's actually happening is that the light from the outburst, this initial kind of big brightening and fading of the star, is passing through dust and gas that was already in the circumstellar environment of V838 Mon. And so as this kind of light echo passes through this otherwise invisible and thus spooky gas shell of V838 Mon, we actually illuminate the structure of the mass that was previously ejected. That's really cool and also really spooky. Trust me. We can also do this for other types of stellar outbursts. My favorite example is with supernova. So a supernova is a star that explodes. It gets incredibly bright during this process and then fades over the course of months and years. Now, just like the outburst of V838 Mon, if we happen to get lucky and there's a dust sheet between the explosion, pictured here, and us, then we can actually see, when we look at this projected onto the sky, these expanding rings, these expanding light echoes from the explosion, just like with V838 Mon. Okay, this is kind of like a boring diagram. Let's actually look at some data. This is a real astronomical image showing expanding light echoes. Each one of these little red lines is an individual light echo. And if you look and you measure the brightness of these light echoes as a function of time, and you can and look at the brightness of different light echoes as they pass through different dust sheets, you can actually reconstruct the original explosion. So this example was just a really pretty and thus really great to put on this slide example, but Armin Rest, who used to be a UW Astronomy graduate student, has done this kind of work for historical supernovae. And so we can actually trace the explosion and evolution of stars that died 500,000 years ago, which is really, really cool. All right, let's move on to the mystery of Hani's Woolwork. I'm going to take you all back, way back to 2007. This is the logo for a project called the Galaxy Zoo. So the Galaxy Zoo is one of a series of projects that's available on zooniverse.com. If you are all interested in citizen science, go to zooniverse.com, check it out. I don't work for Zooniverse, I'm not on any of these teams. It's just really cool. I go on and do it all the time. It's really fun. So Zooniverse has citizen science projects in all kinds of different fields, not necessarily just astronomy and physics, but also really fun stuff like the arts and biology and history, right? And if you go to the space tab, you'll see projects that look like this. These are kind of the oldest projects that are on the Zooniverse. More recent ones, though, are being posted all the time, so it definitely behooves you to go on and check it out over and over again. But we see things like the Galaxy Zoo, which we'll talk about in a bit. You can hunt for planets, you can hunt for gravitational wave blips and actual LIGO data, all of these are with actual scientific data. And it looks a little bit like this. I took this screenshot the other day. If you go into the Galaxy Zoo, you'll be shown a picture of a galaxy that looks a little bit like this. This is, again, real data, in this case from the Sloan Digital Sky Survey. And you'll get a chance to classify this image. You'll say, oh, it looks kind of smooth like this. Maybe it has some features, not really. Doesn't look like something weird going on with the telescope. You'll kind of go through this series of classification steps. All right, Q. Oh, I had this number written down. IC2497. I had that memorized, I promise. So IC2497 is this beautiful galaxy here, but in 2007, the best image we have of it looked like this. This is kind of data similar to what people on the Galaxy Zoo would have looked at the time from the Sloan Digital Sky Survey. Here's the galaxy, it's kind of blobby and yellowy and has some fun stuff here. And then here's this thing. This thing, I'm looking, this thing. This spooky, spooky space ghost. So in 2007, a Dutch school teacher named Hanny van Arkel was on the Galaxy Zoo. And if you have a membership on Galaxy Zoo, you can post on the forums there. And so Hanny said, hey look, I found this voorwerp, which is Dutch for object. I found this thing. It's blue. What's going on? And my favorite response is, I don't know, like a cloud or something? But the answer is even spookier. So, the Galaxy Zoo team was notified of this weird voorwerp, and they decided to go get follow-up imaging with the Hubble Space Telescope. And they found this. So here's IC2497, and here is Hanny's voorwerp. Weird, right? This thing up here, this kind of clump here, is a clump of stars and gas, kind of newly formed stars. But all of this light here is not enough to be explained, or the star forming region here, rather, is not enough to explain this glowing light. And so scientists were able to figure out that this light, or this gas, rather, that was glowing because it was photoionized, which is a very big word that just means there's some light zapping it, and then it glows because the light's zapping it. So, scientists took Hanny's voorwerp and made some measurements, and it does not matter what these axes are. All that matters is that all these gray points are measurements from gas that's being zapped by different sources. And these black lines separate this gas separate the sources of the zapping into three different regions. One is gas that's being zapped by stars, which is really boring and not at all spooky. The other is this thing called the LINER region, which is kind of spooky because it's an acronym. And the other thing up here, and gas up here in this region is being zapped by emission of matter falling onto a supermassive black hole. And wouldn't you know it, Halley's Warwarp falls into this region of this plot. It's being zapped by a supermassive black hole. But wait, you say, there's no supermassive black hole here. What's going on? Where is this black hole? See, this is a galaxy, and I know that galaxies have supermassive black holes at their centers, but when we analyzed this galaxy, there was no actively accreting, no supermassive black hole with mass actively falling onto it. So what's going on? I made this really cute schematic. Here is IC 2497. And here is a galaxy. Surprisingly, Keynote doesn't have like really pretty galaxy things. Go figure. So, this galaxy is slightly less massive than this galaxy, and it's going to fall towards IC 2497 and miss, and zoom away, never to be heard from again. But as it does that, matter is going to be pulled, or gas rather, is going to be pulled from this galaxy and get left behind. Some of that gas gets ejected from the system, and some of it falls onto IC 2497, and it falls into the center, and falls onto the supermassive black hole. And when it does, that gas heats up and starts glowing in intense ionizing radiation and zaps Halley's Warwarp until it glows just like this. We don't see any black hole here because the black hole turned off. The gas was all consumed. But the light from that black hole was still causing Halley's Warwarp to glow in intense optical radiation, which is super cool. Alright. So here's what's the really spooky thing. Halley's Warwarp is about 200,000 light years away from the center of IC 2497, which means that it took the light from the gas falling onto the center of this galaxy 200,000 years to reach Halley's Warwarp and zap it, photoionize it. But black holes, right? Remember, this was all from matter falling onto a supermassive black hole. Black holes are about a light year in diameter, and Halley's Warwarp is 200,000 light years away. That's like me holding up the head of a pin and zapping something 4.5 football fields away. I know, it's so exciting. It's so exciting. So, I think that's cool. I think that's spooky. Thank you all so much for listening to me rant about cool, spooky things. Are there any questions? I'm happy to stand here and dance. Yeah. Great, so the question was, is Halley's Warwarp just a cloud of gas, or are there like celestial bodies actually in this thing? So all of this out here is just gas, but this clump over here is actually a cloud of newly formed stars. And for a while it kind of took scientists a long while to figure out how this clump of stars got there. And what we think is that in addition to the light from the gas falling under the supermassive black hole photoionizing Halley's Warwarp, there was also an ejection of gas and other matter from the black hole that slammed into this gas here, and when it slammed into the gas, it caused gravitational collapse of the gas and then stars to form, which is super cool and super spooky.
Why is it green?
Why is it green? Awesome question. So, it's green because it's glowing at forbidden oxygen 3, 5007 angstroms. So basically what's happening here is that there is ionized oxygen, and when you ionize oxygen and put it into this like specific density and temperature regime that this gas is in, it glows in an incredibly strong emission line at this exact wavelength, 5007 angstroms. Ironically, has anyone seen the aurora? Right, a few people have seen the aurora. How many people have seen pictures of the aurora? Great. That glowing green color is this exact same green color. It's the exact same oxygen. When is Night Lunch's next performance? Well, so our guitarist, you may have seen him. His name was Brett. He used to run this event before Nicole took over. He was our guitarist, and then he moved to Switzerland. What a jerk, because he had to get a job. No, he's like killing it. He's awesome. But because he's moved away, we are currently working with some more musicians to try to do more songs, write some new stuff. But if you are craving some night lunch in the meantime, you can go on Spotify, iTunes, Tidal, Deezer, which is a thing. Wherever music is streamed, you can check us out. We're pretty cool, I guess. And spooky. Great question. So the question was, space dust, what is it? Are you like wiping it down with like a Clorox wipe or something? So it turns out that space dust is just kind of solidified space gunk. There are two general kinds. There's carbonate space dust and silicate space dust. That kind of depends on the material that it was formed from. So stars like red supergiants, I think, eject. We have a red supergiant expert in the crowd. Carbonate space dust? Yes. So red supergiants eject carbonate space dust. But silicate space dust, you kind of need some different processes to happen. I think type 2 supernova form silicate space dust. So it's not, it wouldn't wind up looking like a powder. These things can be as small as like tiny little polymer chains of molecules. We do see dust grains starting to coalesce in our solar system into like protoplanets and kind of dusty things like the zodiacal light in our solar system is formed out of dust. Those grains tend to be bigger. But in galaxies, the dust tends to be a lot smaller. Alright, cool. I think that is all. Oh wait, one last question.
Okay. At some point you said something about the black hole going away, and I was like, okay.
Cool. So I said that the black hole turned off. So what's happening is when so when gas falls into a black hole, that gas glows until it gets completely eaten by the black hole. Once the black hole stops being fed, we can't see it anymore. Alright, that is all the time that I have. Thank you all so much for having me.
Alright, let's thank both of our speakers one more time. And I just wanted to point out that next month, due to the turkey holiday, we are going to be at a different day. So Thursday, November 21st at 7 p.m. Please join us for 2 more fantastic talks. Thank you very much. Have a good month.